So welcome back, and welcome to the extension of the metropolis algorithm, which we discussed last week. And what we are going to do now is actually to look at the extension of the metropolis algorithm by introducing importance sampling. So I'm going to take a kind of top-down view first of what we need to code, but I'm also going to remind you quickly about the metropolis algorithm, which we discussed last week. And the importance sampling is normally, the algorithm we end up with is normally called the metropolis Hastings. And but in general, we often just call it the metropolis algorithm. There are some reading suggestions, and the textbook by Beck and Sorella in chapter 3, and in particular these sections 3.4 to 3.9, covers many of these aspects here. And similar also with chapter 4. But before we take this kind of top-down view of what you need to program, I wanted to say something about what we did last week and link that with what is coming now. So let's quickly switch over to the whiteboard and remind ourselves about what we did last week. So let's do that. So if we look at what we did last week, as a quick reminder, let me just write this down here from last week. So what we did was to use the theory for Markov chain. So we have the probability, the likelihood of being in a state I at a time t. And this is something which we could express if we now assume that this transition probability, which we labeled with an uppercase W, where we go from a state J to a state I, this is then multiplied by the probability of being in a state J at a time t prime, which is a previous time. Now, this is the basic equation for Markov chain, and where the new likelihood just depends on knowledge on the situation which we were in the previous time step. And the rest of the prehistory of the system is something which we can access by stepping back. But essentially what we are saying is that the new state of the system at a given time t depends only on the state of the system at the previous time t prime. Now, in the limit, when we now take the limit with t going to infinity, what happens then is if this process converges, then this converges to the largest eigenvalue of that transition probability. And that means that our transition or state, the probability distribution, becomes time independent. Now, the transition probability, which we have defined, this quantity uppercase letter W. So the transition probability this quantity is defined to be normalized, where we now sum over all the matrix elements of the columns. And these matrix elements all sum up to 1. In principle, this quantity which you see here is unknown. And this is the typical situation which we are facing when we are running these Monte Carlo calculations, is that the probability distribution which we assume we know here, or we have a model for it. In our case, this is the wave function squared divided by its normalization constant. And the transition probability, or the probability of making a transition from a state J to a state I, and here we are summing over all the possible states the system can be in, because I mean the ending up in this specific state I depends on all the probabilities of the state which the state can reach at the previous time step. Now, this probability distribution, what we call the transition probability, is something which normally is an unknown quantity, or even if it's a known quantity, it can normally be too difficult to sample from, because it's a multidimensional, multivariable quantity. Now, since we don't know this transition probability, what we did last week was to make a model for it. So we make a model where we split it in terms of a quantity which we called the probability of making the transition. And this was the first term. So if you think of, let's say, electromagnetic transitions from an excited state to the ground state of a system, sometimes these are probabilities or transition probabilities which you can calculate analytically depending on the kind of model and the kind of system which you have. But often this is a very complicated quantity which it's basically impossible to extract an analytical expression for. Or even if you have one, it's too difficult to simulate from it. So we define this one as the probability of making the transition. Making a transition. And then we multiply this with a new probability. So as I said, in a certain sense, since we don't know the expression for W, we are in a way free to model it. And the Metropolis algorithm is based on this kind of split here. And this quantity A is something which we call for the acceptance probability. So that is the acceptance of making a move when you have evaluated transition probability. So we simply call this the acceptance probability. Now, what we did then last week, and this is just a quick summary of the Metropolis algorithm. So we used detailed balance. And detailed balance, what that means when we now have established equilibrium, is that there is a ratio between the probabilities, which we can calculate. And the nice thing with this left-hand part of the equation is that we know the probability distributions, we have a model for it, and taking the ratios here means that we don't need to evaluate the probability or the normalization constant. So when we did this, what we obtained was a transition probability from I to J, or an acceptance probability multiplied with T I going to J, and this is divided by the A of J going to I and multiplied with T of J going to I. Sorry, I think I have interchanged things here. Just a moment, I messed up here. Sorry for that. I was a little bit too fast with setting up the transition probabilities here. So what we have here is the probability of making the transition from J to I and multiplied with J to I here, the transition probability, the acceptance probability of going from I to J, and then again, the probability of making the transition from I to J. Now, the thing which we did last week was simply to now assume that these transition probabilities are reversible. So we simply put them equal, and that simplified the equations, and we ended up with a standard Metropolis algorithm. Just quickly repeating here what we did last week. So we got an expression for making this transition probability from J to I, which was simply the minimum of the ratio between Wi and Wj and 1. And that was the basic Metropolis algorithm, which we set up last week. Now, what we are going to do now is to make a model for this transition probability T. Now, the thing which we did last week when we implemented the Metropolis algorithm, in order to accept a step, we performed a suggested move, but that move was a move which did not follow the transition probability or the distribution probability. So the transition probability which we were using last week, it was a very simple one based on a uniform distribution, and it does not follow the model which we have for the probability distribution. So that means that what we did last week, just to put that back again, so suppose now you have a Gaussian distribution and you want to sample from that one. The distribution looks like this. So you have some points here, and then obviously you want to reach the maximum probability distribution. So if you started with a point x0, you would typically make a step to a new position, x1, which obviously gives you a higher probability, but we have also to jump into lower probability, so we could jump to some position x2 here, and these new positions, x1 would be given by x0 plus some parameter which we just call epsilon, which is set by us, and multiplied by a random number. So this random number is selected between 0 and 1, and it's calculated using the uniform distribution. So just to quickly remind you of that, the uniform distributions gives you, obviously, uniformly distributed numbers between 0 and 1. So this is the uniform distribution. So the points which you would pick then give you points between 0 and 1, but then we subtracted 0.5 because we wanted to have negative numbers as well. So clearly if r is smaller than 0.5, this becomes a negative number. Now, the point with the simple sampling which we did was that this becomes a parameter which we fix. So we fix this to a given value. The R values which we have here are selected according to a uniform distribution. So that means that the way we are jumping in the space of all possible outcomes is something which is not dictated by the way the probability distribution looks like. So that means that I could actually, if I make epsilon very large, I could jump out, if I stay here, I could jump into regions where the probability distribution is equal to 0. This is not wanted because when we are running the calculations, what we want to do is to evaluate the following integral. So suppose now we are calculating the expectation value of a variable x. So this is just the mean value, mu of x. And if we use this kind of standard physics notation with the bracket symbols, this is now given by an integral where x is now given by a specific domain of possible values if we have a continuous distribution, and then we would have a p of x multiplied with x and d of x. Now, suppose now that when you're doing the sampling here, so this reduces to us actually calculating 1 over the number of Monte Carlo cycles. I'll just use this variable MCS for that. So we would have a sum over all the possible Monte Carlo samples where we now pick randomly points x of I. So if we have a function which we want to integrate now, for instance, or we want to find this value x of I, and we are using the uniform distribution. So suppose now that we want to calculate the expectation value of a specific function. So the mean value of that one, and that integral is going to be given by the probability distribution P of x, f of x, of d of x, which we then approximate in the simulation with a loop over the number of Monte Carlo cycles, and I, and then we simply have f of x of I. So this is a typical quantity which we end up evaluating when we now are calculating the expectation value of the energy. So suppose now that this function is a function which is defined between 0 and 1, just as an example. So we have 1 here, we have the x values here, and then our function peaks between 0.4 and 0.5. And suppose now that this, as an example, the function looks like this. Now, if I'm using a uniform distribution, and I select points now between 0 and 1, so this is the uniform distribution, it's 1 here, so P of x here. Now, if I select something like 1 million points randomly, so this will be random variables, x, which I select from this distribution, then since this is a uniform distribution, it's going to give me something. If I have 1 million points I'm selecting, and if it's uniformly distributed, it means simply that it's going to give me 900,000 points in a region where the function itself is 0. So that means that when I'm evaluating this integral here, I'm evaluating an integral where, with 1 million points, I'm only having 100,000 points where this integral is, or this value of the function is non-zero. So it means that I'm wasting away 90% of my Monte Carlo cycles, or my suggested moves. So coming back to what we are doing in a typical Monte Carlo sampling of a quantum mechanical quantity, what we have then is a probability distribution. So this could be the wave function squared, which is our model. But then if I select this number here to be too large, I may actually be jumping in and out of regions where the wave function squared is actually equal to 0. So when I then sample these points, I will have lots of contributions where this quantity I'm interested in is just 0. So simply what I'm doing then, by this kind of brute force approach, as we've been calling it, by selecting these points here, or this variable epsilon, is that we may be unlucky and be in a situation where the points which we pick randomly just give us 0 contributions. And this is where importance sampling comes in. That's the main reason why we're actually dealing with importance sampling, because now we want our distribution to dictate how we select the points. Now, another thing I wanted to say is that this constant epsilon, which you see here, is often fine-tuned in the brute force approach by simply saying that we toss the coin. So we give a 50-50% of accepting, not accepting. And that means that we often tune this one so that you have a kind of ad hoc rule, that you tune this one so that you roughly accept 50% of the moves. So still, this is a very ad hoc rule because we don't know exactly what the value is. And then you would simply tune it with just a coin flip, which is just a random outcome when you don't know anything. And this is very inefficient because it simply means that there will be a lot of samples which you will have to discard because they just give 0 contributions. So what we want to do then is to do something which is a little bit more intelligent, and then have a transition probability which now reflects the probability distribution which we are sampling from. So this is the essence of importance sampling. So let's take just a quicker look at this and look at how we can modify the Metropolis algorithm by now assuming that this expression here is no longer valid. So the importance sampling part which we are going to deal with is us trying to find a model for this transition probability. And this is a model which will be modeled by the Fokker-Planck approximation. And that will give us a way to pick points where we hopefully now sample from points where the distribution is non-zero, so that we don't waste CPU cycles. It's going to require some more CPU cycles because we would have to evaluate this probability distribution. Still, what we are going to deal with is actually ratios of probabilities. So if you look at the acceptance probability now, this is an equation which is going to change by us multiplying out the function t. So let's look at the modified ratios of probabilities. So what we are going to get then, if we now want to model this A of j going to I, and A of I going to j, this is still the same ratio. So we have Wi divided by Wj. And then you see if we now go back to the equation which we had, we simply need to multiply up Ti going to j and Ji going to I. So what we're going to get then is simply this multiplied with I going to j and the case with j going to I here. So this is now going to be our new ratio, and that leads to a modified Metropolis algorithm, and this is normally called the Metropolis-Hastings algorithm, where we now are going to evaluate the minimum of this ratio here, Wi, of Ti going to j, and then 1 here, and then divided by Wj of T of j going to I. So what we will need then is a model for this transition probability. And that is what we are going to look at now. before we do that, I wanted to say a little bit more about the mathematics of importance sampling. So this is now the modified Metropolis algorithm, and it's normally called the Metropolis-Hastings algorithm. So the Monte Carlo machinery, the Monte Carlo algorithm, the general one, is us performing a loop over all possible Monte Carlo samples with all the moves which we suggest. So we fix the number of Monte Carlo cycles. And then when we propose a new position or a new state, then we use the Metropolis algorithm to accept or reject the suggested move. So this is in essence what we actually going to end up doing in this course here. So in our case, what we are going to try now is to find a model for this function for t of j going to I based on the trial wave function on psi of t, and where this is now given by a variable r, where we can put a label I here, and this label I simply represents the possible positions where the particles are in, or the state. If we need more quantum numbers, we could add that. And then we have the variational parameters, which we simply label as an alpha here, or as a theta. And I put a vector sign on it just to indicate that this is normally a vector of a given length, which is defined by the number of variational parameters which we are dealing with. So we defined already the way the integral looks like, and if we take the basic uniform distribution, then this is something which can quickly lead to a very inefficient algorithm. So what we are going to do now is simply to look at some basic mathematics of importance sampling before we then go back to the Jupyter notebook and take a top-down look at what we need to implement numerically in our programs. So let's remind ourselves, and some of you may have seen these things before, what we will call the basics of Monte Carlo integration. So this is a stochastic integration, and we're just going to start with the simplest possible case where we have an integral which is defined from 0 to 1, and this is the function f of x of d of x which we want to evaluate. Now, from the theorem of one of the fundamental theorems of calculus, this function here is something which we can also define as the average value of a function. So this integral is also the average value of this function, which is now given by some f of x of p of x of d of x. So let's quickly remind ourselves about the uniform distributions if you're not familiar with that, or if you have forgotten about it. So let's just set up the uniform distribution, which is one of the simplest possible ones which we can deal with. So the uniform distribution is, if we make a plot of it, is typically defined in a domain between x equal to 0 to 1. So if we plot it here, this is x, and 0, it is given by 1, and it is simply 1 over the whole domain here. So this is simply the uniform distribution, and this is the function from which we will extract random numbers. What you should also keep in mind is that the basic random number generator is actually based on the uniform distribution. So if we have a slightly different integral, we would have to make a change of variables. So that's one of the first things which we often do then. If we now write it out, the uniform distribution is going to look like this. It's d of x when x is between 0 and 1. So let me just try to write this better. So we have 0 less than x less than equal than 0 and less than equal than 1. And then it's equal to d of x, and then it's 0 else. So this is basically a pretty simple definition of the distribution. So if I have something like, suppose I do 1,000 Monte Carlo cycles, define that as my number of Monte Carlo cycles, which means the same as the number of random numbers which I will extract. Ideally, the uniform distribution should then distribute, if this goes from 0.1, if I pick 1,000 points randomly, I should have 100 points in the first slot, I should have 100 points in a new one, etc., etc. Now, normally this kind of evenly distributed points or uniformly distributed points is something which you will start seeing when you add more and more points. So with 1,000 points, you may actually have, let's say, 88 or 90 in the first slot, and then there'll be maybe somewhat more in the next one, etc., etc. So when we are now calculating these integrals, let us also quickly remind ourselves of some of the properties of these probability distributions. So for the uniform distribution, I would have an integral from P of x d of x, which has to be normalized to 1. If I then look at the expectation value of the function which I'm looking at, f of x, if this is a function I want to integrate, so this expectation value by one of the fundamental theorems of calculus is something which I can rewrite like this. And this is f of x of d of x. And this is nothing but the expectation value of the function f of x. So for the uniform distribution, this is a function which I can easily calculate. Especially, I can calculate many of the properties of the probability distributions, like the mean value of P of x has obviously to be equal to half. I can calculate the variance of P of x, etc., etc. So another function which is very interesting for us is something which is called the cumulative function. And that is a function where we now integrate from, suppose now we are looking at a more general probability distribution from minus infinity up to point A. So we have P of x of d of x, and the cumulative function is a function which is defined so that if B is larger or equal than A, then what applies is that we have an integral P of from infinity to up to B, which gives a larger value than the integral from minus infinity to A. So one of the first things which we need to do, if we have another type of integral, suppose now that we are dealing with a probability distribution which is not the uniform distribution, but we have a probability distribution which is given by the exponential distribution. Now, in this particular case, x is defined from 0 to infinity. And if we now want to perform a calculation where we use this probability distribution, this leads to problems with the simply because with the calculation, because we haven't defined the way we can calculate the random numbers using this particular distribution. So what happens then is that we end up with having to have a change of variables. The main reason for that is that the random number generator, RNG, this is a typical acronym which you will find in the literature. Basically, all these algorithms, the RNGs are based on the uniform distribution. So the basic algorithm is actually this one, and then you have ways to transform from the uniform distribution to another domain of variables. So that means that we need to change variables. So suppose now that we look at one specific example, like this exponential distribution. And let's just change variables because we will restrict x to the uniform distribution. So suppose now that we have a probability distribution which is given by the variable y, and this is now given by the exponential distribution. So this simply is the probability of an event y in an interval between y and y plus d of y. This is the way you would read that one. And y is now defined to be a variable which lives between 0 and infinity. So there's a very important aspect here, and that is that probabilities have to be conserved. So if I now have my uniform distribution, which I labeled with a p prime, for instance, or just any other probability, if I make a transformation of variables, the probability should be conserved, because else you could find a smarter probability which makes you a lotto millionaire. So probabilities are conserved. And so let's now assume that this is just our uniform distribution, which is the base distribution, which is typically used in all generations of random variables. So this is a uniform distribution, and that means that this simply reduces to d of x when x is between 0 and 1. So we're going to draw points from that one. This means that when we now set up things, we can, with this expression here, if we now have p of y of d of y, we require that this is equal to d of x. And then we can integrate up this expression. So we can then have an integral for x of y as a function of y. And that gives us an integral, which is nothing but the cumulative function for the probability y. And then we have a minus y prime multiplied with a dy prime. Now, this is an integral which we can calculate easily. And we know that this one is equal to e minus 1 minus e to the minus y. Then I can switch so that I can define y as a function of x. And that gives me minus ln of 1 minus x. And you see now quickly that when y is equal to 0, it's equal to 0 when we have x is equal to 0, because if I put x equal to 0, I have ln 1, which gives me 0. And then it's equal to infinity, which is the other extreme, when x is equal to 1, because then we have log of 0 and minus log of 0. So this is actually going to give us infinity. So what we have done now is to make a mapping to a new domain where we have a variable which is defined from 0 to infinity. So this is a typical example of a change of variables. Now I can give you another example here. So let's just look at that one so you gain some confidence in doing this. Suppose now that I have a function which I have made here, which is p of x, which is 1/3 multiplied 4 by 4 minus 2x. And this function here is not the uniform distribution, but still it lives between 0 and 1. So this is just a probability distribution which I have mocked up. And it behaves like a probability distribution, but let's just wait a little bit so you can write down the last equations which we put up here. So you will see that when you now put in some of the requirements for this to be a probability distribution, you will typically see that this is a function which is increasing. It's a function which is normalized to 1. And you will also see that the cumulative function behaves as it should for a probability distribution. So I'm not repeating all these basic elements of statistics, like the cumulative function. Then what I'm going to do now is simply to ask myself, what kind of mapping would I now need from a uniform distribution to this new distribution, which I would like to use now because I'm going to integrate a function which is almost equal to this function here. And this, the reason why I'm doing this is because I want to motivate important sampling by looking at some simple examples. So if you now look at the uniform distribution, so I define a variable y, which is now given by the uniform distribution, and y lives also between 0 and 1. So this is a simpler case compared to the exponential distribution. But we assume now that p of y this is just a uniform distribution. And I use the acronym PDF, which is a probability distribution function. And then I know that I can sample these variables y from the uniform distribution. Now, what I can do now is that I can actually do the same exercise which I did before with the exponential distribution. So I'm going to set these distribution to be equal. So this means that I will have 1 divided by 3, and then I have this function which gives me 4 minus 2x. And this is my probability distribution, and this is going to be equal to d of y. So I can now integrate up, and what I will find then is that when I have integrated up, I get a new function, so I can actually express y of x in terms of a function which is 1/3 of 4 minus x times x. So this is my new function, but now I can invert that one to give me x of y. So when I now have x of y, so I'd leave that as a small exercise to you guys, and what you will see then is that when y is equal to 0, then x is also equal to 0. And when y is equal to 1, then you will also have that x is equal to 1. So this is just another type of mapping. And the reason why I'm doing this now is that I'm going to look at how I can use this new probability distribution to actually introduce importance sampling. So if I do this with this simple example, you may ask why I did that for the last case. Now I want to introduce importance sampling. So with importance sampling, if we now look at an example, let's suppose now that we want to integrate the following function from 0 to 1. And I want to integrate d of x of 1 plus x squared. And some of you may have seen this function. So this is actually our function f of x of d of x. And this function is a function when we integrate it, which gives a famous result. So if I had taken a factor 1 divided by 4 in front of it, I would actually have gotten pi. So this is a well-known integral. So if I now look at a slight modification of this expression, I could now introduce a probability distribution by redefining the function I want to integrate by simply rewriting this as an f of x divided by p of x times d of x. So this mimics a little bit of what we've been doing with the local energy. Now, the probability which we want to use now is a function p of x, which is this new probability, which is 1/3 divided by 4 minus 2 of x. This is actually interesting because if I now look at the ratio between this specific function here and the function at the endpoints, these ratios are going to actually be given by a constant. So the interesting thing now is that if we can find a probability distribution here, which is so that the function we want to integrate divided by this probability distribution is close to a constant, then what we end up with then is just a constant here multiplied with the probability distribution. And since this is normalized to 1, this is just going to give us a constant. So let's take a closer look at this specific function. So if I look at the function value at x equals 0, divided by the probability at x equal to 0, this is actually equal to, if you plug in the values, to f of 1 divided by p of 1, the other endpoint, and that is equal to 3 divided by 4. So this is a constant. So if you plot this ratio, what you will see is that in between 0 and 1, it's not exactly constant, but it is almost constant. So that the thing is then the ideal is that you can find a probability distribution which follows the function you want to integrate. The ideal is that f of x of p of x is actually a constant, is equal to a constant for all x. So what does that mean for us then? So it means that we are now setting up an integral from 0 to 1 of p of x, so where we simply have just made a slight modification, where we now have a new function f of x of d of x. And this function f of x, which we have here, uppercase letter x, this function is actually given by f of x divided by our p of x. Now, if that is a constant, then this integral simply reduces to 1. So that means that if I do that, then this is a constant. So the ideal, we want this to be a constant. And if we have that, then the integral simply reduces to the normalization of p of x, which is, and we have assumed that the integral is normalized. So that just simply gives us a constant. So let's just write it out. So that means, suppose now that is a constant, this reduces to f of x, p of x, multiplied with this uppercase letter x, and d of x, and that's just a constant multiplied with 0 to 1 of p of x, of d of x, and this quantity here is the normalization criterion which we have, so this is just equal to constant. So why is this interesting? Now, this is now interesting because when we are calculating the variance, so what we have is that the integral which we evaluated now is the expectation value of this quantity. And let's try to finish this before we take a small break. So we have p of x of f of x of d of x. And this mean value now is just given by the constant. But what becomes more interesting is that if I calculate the variance of this quantity f of x, this is nothing but 0 to 1 of the probability p of x. And then I have the function f of x minus, and then I have e expectation value of f, and this is squared and multiplied with d of x. Now, the interesting thing now is that this gives us the following. So if we write it out, then we are just going to get a quantity which is going to be given by the integral over f of x squared, uppercase letter f of x squared, minus the expectation value of f squared. So what we will have then is a result which is going to be given by the expectation value of f of x squared minus the expectation value of f of x squared, which is just the mean value. Now, this quantity here, so this, if it's a constant, then this is just a constant squared. If you look at this expression here, this is going to be an integral over p of x, and then I have f of x squared of d of x. And if f is a constant, this is just going to be the same constant squared. So what we end up with then is the ideal. So we have a variance which is actually equal to 0 when we evaluate this expression. And that means that the standard deviation is 0. So we have no error in the evaluation. Now, in principle, we will not be able to find a probability distribution which is something which gives us a constant expression. But what we will get is something which is a probability distribution, this probability which we have defined here, which hopefully follows to a large extent the function we want to integrate. This is important sampling. And keep in mind also that when we perform this important sampling, when we are doing the actual calculations, we have to call the random number generator, which is now defined for the variables y, which we defined here, which are given by the uniform distribution. So there will be a mapping with a uniform distribution inside the calculation of an integral like this. So when we now evaluate these integrals, this ratio here between the function we originally had and the probability distribution is normally not a constant, but hopefully the probability distribution which we have defined here follows the function in a meaningful way or in a decent way. This is essentially some of the basic mathematics which we want to introduce in these type of calculations. And this is why important sampling is actually so important. So let's just wrap this up and go back to the mapping which we did. So we had this probability distribution, which now follows the function. It's constant in the both ends when we take the ratio. But when we now are evaluating the integral, so what we had, so let's just quickly finish this and then we take a break. So we have an integral I, which is an integral from 0 to 1, and then we introduce this probability which follows the function f of x divided by p of x here and d of x. And in our case, we had a probability distribution y, which is the uniform distribution from which we are going to extract the random numbers, but then we need to make a mapping from that one to the new distribution. So when I'm now setting up the integral, what I'm going to have is a mapping between the two probabilities, the uniform distribution and the new one. So it means that our integral then is actually going to be given by, and since we have the uniform distribution now, originally we had x from 0 to 1. Y is also defined from 0 to 1. So this is the function we are now trying to evaluate. But now we want to perform a mapping from the uniform distribution to x. So what we have then is that this integral changes. Now this is a case where the integration limits stay the same. But in general, the integration limits which you have here will not be the same as the one you have when you have the uniform distribution. So the last line here is actually us looking at the uniform distribution. So we would then have x of y, and where the random number generator is the one which defines y here. And the random number generator is now just the uniform distribution. So often, if you see this letter u here, that is meant to refer to the uniform distribution. And then we have this probability distribution which follows the function, which is given by this variable x, but we need to make a mapping from x to y, and our final integral is this one. So we used actually that p of x of d of x is equal to d of y. Now, the hope then is that when we now do the Monte Carlo sampling with this specific function, that we will actually get a result which is much better and with a much smaller standard deviation. Because when we run the Monte Carlo calculation, what we end up with is just a set of samples where we call the uniform distribution. And by doing the mapping, if we have found a probability distribution which follows the function, it means that we, although we will never get the ideal of a constant here, we can get something which gives us a much smaller variance. So when we are running Monte Carlo calculation, the ideal is actually to reduce the variance by some smart tricks, because the variance tells us the deviation from the mean value. So we have the mean value plus the standard deviation, and we would clearly, we want clearly to reduce the standard deviation. For the Monte Carlo samplings, which we are going to do, reducing the or having a smarter way to sample the points is also something which will then, if we look back at this figure which we put up a little bit earlier here. So if you look at this equation, this figure here, what we want to have is something which samples only the relevant points where the integrand is non-zero. If we were to sample points from everywhere here, we would have a huge collection of points which are just giving us zero contributions to the integral. So that means that we would waste a lot of CPU cycles. So importance sampling, which is then reflected in this new metropolis test. So if we go back a little bit to what we started with, the new metropolis test now is going to include a function t here, which hopefully is going to give us random variables which follow the distribution we want to integrate so that we don't waste CPU cycles. So the kind of brute force approach which we looked at last week is very easy to implement, but at the same time, it can easily lead to us wasting a lot of CPU cycles and sampling from points where the distribution is actually equal to zero. So it fits now to take a small break. And I would suggest, since we are online here, that we just start in 10 minutes again. So we start at 10, 17, 18 something, and then we just take a quick break now. So after this very quick background about Metropolis Hastings, about importance sampling, change of variables, and so on, we will use some very simple examples to show you how importance sampling hopefully can give us a better evaluation of expectation values. So one of the kind of holy grails in Monte Carlo sampling is actually to reduce the error in the calculations. So if we can sample in a more meaningful way, this often means that we will hopefully get a better standard deviation. And even though this kind of brute force approach where we tune the step length, that is how the random walkers jumps in the space of possible positions, is very easy to implement, it becomes inefficient because we can risk to end up sampling from regions where the function is actually just zero, the one which we want to integrate. So a recipe which is used and where we will look at the mathematics in more detail next week. You will find a lot of the material here, but I wanted to discuss these things in a slightly more detailed way next week. So what I'm going to do now is just to give you the kind of top-down approach of what you need to program. And this is relevant for the project because what we would like to suggest now is that you try to implement this brute force in Monte Carlo sampling, the Metropolis algorithm, without using a importance-guided selection of configurations or points in space. This is the easiest thing to implement. And then after you've done that and you have a code which functions, the next step is in the coding is to include importance sampling. This is something which will normally give us a much better sampling, and it will also typically reduce the standard deviation of the calculations so that we have a better estimate of the expectation values, which in our case is the mean value of the integral we want to evaluate, and that mean value is the energy of the system. So what we are going to do, and we are going to take a top-down view on it, is to start with something which is called the Fokker-Planck equation. So the Fokker-Planck equation is something you can read as an extension of the standard diffusion equation, where you now can think of, in addition to the standard kinetic energy term, which is the second derivative, you have a term which represents some force which makes, let's say, a particle, suppose this force is a gravitational field. This could just be something which expresses the drift in the gravitational field. And that means that since we know that the acceleration is proportional to the force, and we know that the derivative there of that quantity there has to be something which is connected with the velocities, so how the force actually affects this equation here. So we have the second derivative of the velocity here. and then we have the derivative with respect to the spatial coordinates of the force here. And this is then multiplied with a probability distribution. So when equilibrium has been reached, then this t, which you see here, becomes irrelevant because then there is no time dependence anymore. So this f is normally called a drift term. And in statistical mechanics, if you're looking at classical systems, this is an equation which has been widely studied, the Fokker-Planck equation. So you can think of this as a modification of the standard diffusion equation in the presence of some external field, which acts on the object you're looking at. Now, important sampling, the thing which we're also going to discuss in more detail next week is the equation which is linked with the Fokker-Planck equation, which is called the Langevin equation. And this is a differential equation, which then allows us to find the next position through the Langevin equation when we integrate this equation up, where we have a force which acts on the motion of the particle, and then you could think of having some kind of random fluctuations. So in essence, this is an extension of Newton's law in the presence of some kind of random fluctuations, which often are thought of varying much, much faster than the force here. So the random with a new random value, a new random variable, when you integrate up this equation, and I'm just stating the answer here, we can then define a new position x in terms of x, the previous one, which now includes this force, the drift term, multiplied with a step size. So what we are using here is just the simplest possible way of updating the points by solving this differential equation. We will then simply keep the first derivative. So we get a delta t, and then we have some random fluctuations here, which were epsilon typically is a Gaussian random variable, and delta t is a chosen step. So we are going to discuss the derivations of these equations here in more detail next week. But now I'm just going to take this, as I said, this top-down approach, and we are simply going to look at the equations which we will need to program. So in our case, this f of x is going to be defined by the probability distribution. That means the wave function squared. And in the context of the Monte Carlo sampling, we often end up calling this f for a quantum force. Sorry, a quantum force. Please excuse me. The quantity d, if you do this in atomic units and you put the h bar and the mass of the particles all equal to 1, this simply becomes equal to a half. So when we are dealing with a quantum mechanical sampling here, this d, and you have dimensionless quantities, this d is actually equal to a half. And delta t can be viewed as a parameter. So what you would typically do then is to run calculations with different delta t values and try to find the one which gives you the best result for both the standard deviation and for the expectation value. So it is a parameter in the calculations. And normally the chosen values are between 10 to the minus 3 to 10 to the minus 2. If you make it too small, then the jump in space you will make will be very small. And that means that you will basically stay close to the same point where you started. And that means you will not be able to sample larger parts of the functions you want to integrate. If you make it too large, suppose you have it to 0.1 or 1, then you will be jumping in and out of the probability distribution. And that will also give you poorer results. So the important sampling, if you now you can think of this in a classical terms. And if we now just split this in terms of various components of this force F, you would typically have this as a sum over the different components of the velocity. And so this ith term is just a component of the drift, of this drift term, which can be caused by some external potential. And d is this diffusion coefficient or constant. So this is the equation we want to simulate. And when equilibrium has been reached, then P is time independent. So we are going to assume that after some samplings, and this leads also to a concept which is called burn-in in Monte Carlo sampling, that typically we may not start with the most likely distribution. We will need some Monte Carlo cycles before the equilibrium situation has been reached. So it's pretty common then to throw away the first 5 to 10% of the Monte Carlo cycles. You can actually calculate when this most likely situation has been reached. And when that is the case, that is when you would start accumulating points to the evaluation of the integrals. The probability distribution, when it's time independent, it means that the left-hand side of the equation here has to be equal to 0. And if you do that, you can actually find a requirement for this, how to satisfy the right-hand side. And that simply means that the second derivative of the probability distribution simply has to equal the probability distribution times the derivative of the drift term, or the force, and times the force multiplied with the gradient of the probability distribution. So it should be pretty trivial actually to see that this is actually the case, because you have to basically just use the chain rule for derivatives. And then when you do importance sampling, you can then see mathematically that the drift term has to be of the form of some function here multiplied with the derivative of the probability distribution. So if you do that, then you can simply show that when you calculate this second derivative, these are the equations which you then would have. And this is only possible if G is equal to 1 divided by P. It's pretty straightforward to see that if you look at these equations and then require that you have to fulfill this relation which you see here. Now, this means that if we now allow P to be the quantum mechanical distribution, which is the wave function squared, then you will find that if this is a wave function squared, you will then find, since this is 1 over P, that this function f has to be equal to 2 divided by the trial wave function times the gradient of the wave function. So this is known as the quantum force. And this term is responsible for pushing the walker towards regions of configuration space where the trial wave function is large. And that means that when you increase the efficiency, this will actually increase the efficiency of the simulation in contrast to what we call the brute force algorithm, where the walker has the same probability of moving in every direction. So you can think of this drift term, which is now related to the quantum mechanical wave function, as something which pushes the walkers in the right direction. So importance sampling then is us now going back. So if you look at this expression here, this is one of the cases. If we now go back and insert this in the Fokker-Planck equation, which is the equation you see here, this is an equation which we can solve with approximations, and we can find the solution to that problem. And these are also things which we will discuss in more detail next week. We can then obtain an expression for this transition probability, which is the so-called Green's function. So this is going to be the function t, which expresses the probability of moving from a position x to a position y in a time step delta t. And this is actually given by a Gaussian, but it contains now this quantum force. So if you did not have, so for those of you who have studied these type of equations and are somewhat familiar with Green's functions, you may know that if I take away the drift term in the diffusion equations, if I take away this one, I actually have a solution for the probability of moving from x to y in terms of the unperturbed Green's function. And that is simply given by the same expression here, but with f equal to 0. And that gives us a Gaussian where you have the exponential of minus 1 minus x squared divided by this quantity here, which then plays the role of a variance. So you can actually show that the diffusion equation without this drift term has as a solution a Green's function, which expresses the probability of moving from x to y in terms of this function here. And you see that this is actually a probability distribution. If you take away f, it's just a Gaussian distribution, which then has 4D, no, actually this quantity which you see inside here, and since we have n particles, then we need a factor of 3.5, and this is in 3 dimensions. If you are in 1 dimension, it's obviously 1 times n divided by 2. In 2 dimensions, it just simply becomes n. So that means that when we now are going to modify the Metropolis algorithm, that means that our brute force Metropolis algorithm, where this q was just a ratio between the wave function squared, is now replaced by the Metropolis Hastings algorithm. So which then gives us a probability distribution. And since this one will depend on the value of the force, either at x and y, it means that these quantities here, you cannot cancel them away because, or factor them away because they are different when we go from x to y or when we go from y to x. So this is now our model for the transition probability, which follows the ansatz for the wave function. And it's then something which where we need an extra calculation, and that is a calculation of the gradient of the quantum force, or in our case, the gradient of the trial wave function. So this is an additional derivative which we now need to include, and obviously that leads to more CPU cycles because we have to do more calculations. So when we now look at the code, and this is roughly where we will stop today, this is an implementation of not the same situation which you are looking at, but it's actually a 2-electron case where the electrons interact with a Coulomb interaction. And in that case, we have 2 parameters, and we are coming back a little bit to why the trial wave function looks as it does. So it's not exactly the harmonic oscillator, but it is a system with 2 electrons in a harmonic oscillator type trap, where the 2 electrons then also interact through a Coulomb interaction. And that gives a slightly more complicated trial wave function, but the basic philosophy of the coding here is the same as before. You have a wave function, and if you just have a harmonic oscillator, in this case I have 2 particles, particle 1 and particle 2, which you see here, and they live in 2 dimensions. So 0 is x and 1 is y. And the first element of this array refers to the number of particles. So particle 1 has element 0 in this array, and particle 2 has element 1. So this is just a simple implementation of a 2-dimensional position for 2 particles in a very brute force way. And then there is something which we are going to look at a little bit later, which we call a Jastrow factor. And this gives us a slightly modified wave function and also a slightly modified local energy, but we can still calculate it analytically. And this is what I have done here. It's a slightly more complicated expression. Then I need to calculate the derivative of the trial wave function. Actually, what I'm doing is to calculate the gradient. So this quantity, quantum force, is now the gradient. And I need to calculate that one. And in this case, due to the form of the wave function, I have a slightly more complicated quantum force, but I'm setting up these derivatives here by using analytical expressions. And this is something which you would also have to do in the setting up of the code. So you would actually need the gradient of your trial wave function, which, when you just look at the harmonic oscillator, is quite simple. If you add interactions, it becomes a little bit more complicated, and this is the case here. When you're now doing the Monte Carlo sampling, we now need to update the points using this Langevin equation. So I define a time step, which is 0.05. So this is just a trial value. I set up my random number generator. I'm looping over the variational parameters. I have 2 in this case. And I start my Monte Carlo machinery by looping over all the possible cycles. I'm setting up the initial positions because now I'm actually having more than 1 particle. And you see now that I have a normal distribution, and I'll multiply this with a the square root of the time step. So this is just my initial position. There's no quantum force here. And my old wave function is calculated with the old position, and the same with the old quantum force, the initial one, is just calculated with this initial position, which I call position old. So these are additions which you now need to make. Now, also pay attention to that in this code, I move both particles and do the sampling afterwards. This becomes inefficient when you have many particles, and we are coming back to that next week. So what you would normally do is actually to move one particle at a time. So, and you will see that in this case, sorry, I was wrong, because I'm just moving one particle at a time, and I'm performing the metropolis test by moving one particle at a time. You could actually move all particles, but here I have implemented the moving of one particle at a time. And I will come back to these technicalities next week. But for now, what I'm doing is to propose a new position, and you see now that I have the old position, I have the normal distribution times the square root of the time step, and then I multiply with the quantum force. And the diffusion constant is just equal to 1/2, because I put h bar equal to 1 and the mass of the particle equal to 1. So I have dimensionless units here. And I'm just implementing here the Langevin equation, which just to quickly remind you of that, if we go back again a little bit. So the update is now given by this function here, where I have now the quantum force. So I need the gradient of the trial wave function, and this is calculated by this function quantum force. So this is my gradient, and you see I have it component-wise. So it contains both the x and the y components, because I'm dealing with 2 dimensions. And 0 is particle 1, and 1 is particle 2 here. So these are the analytical derivatives for that specific trial wave function. And you will need to find the analytical derivatives for your wave function without having the interacting term first. So when we do this now, we have now the new position, and we can calculate the new wave function, and then we calculate the new quantum force. Now, the thing which is very useful to do now, because we are going to calculate ratios. So when we calculate ratios, if we look back a little bit to the metropolis test, so let's slowly go back here. It's not convenient to calculate this function, because this function here is actually an exponential. So one thing is that these factors here, they disappear because we are taking ratios, but then we have ratios of exponentials. So what is convenient then is to calculate the argument to the ratios, because you know that if you take the ratios of 2 exponential functions, then you can simply first calculate the arguments of the denominator and the numerator, and then calculate the exponential. That saves a lot of CPU cycles, because calculating exponentials is obviously, it's pretty fast, but it will slow down your code if you calculate them unnecessarily. So what I'm doing now here, this Green's function, what you see here, for the dimensions which we're looking at, this is 2 dimensions, I am simply now setting up the arguments, and you will see that I have I and j here, but I also need to interchange them, because I have the quantum force, new here, and I also have the quantum force old. So one comes from the denominator and one comes from the numerator. So then I'm evaluating the argument to the exponentials of a ratio of exponentials. So when I have the argument, I can calculate the final ratio by simply calculating the exponential of this Green's function. And then the probability ratio is the Green's function, where I now have the calculated the ratio between the Green's function for going from x to y and y to x. And this is multiplied with a wave function squared, the new one, divided by the old one. So this is what I will use in the metropolis test. And then my metropolis test now simply says that if a random number between 0 and 1 is smaller or equal than the probability ratio, I update the new position to so the old one becomes equal to the new one, and my old quantum force becomes equal to the new one. And then with that, I have the new wave function. I calculate my local energy with the new position, and then I update the energy contribution and the energy squared. When I've gone through the Monte Carlo loop, I have all the updates. I divide with the number of Monte Carlo cycles to calculate the expectation values, and I do the same for the energy squared. And with the energy squared, I can calculate the variance, and the error now, though the standard deviation, is just the square root of the variance divided by the number of cycles here. And this is essentially it. And in this specific case, I define two particles, two dimensions. I have number of variables, alpha and beta, equal to 10. So that means I'm doing 100 calculations. And then after this now, I am making a plot. So feel free to run these codes here if you want to. But the essence is that we have a Monte Carlo sampling now, which requires an additional element, and that is the calculation of this quantum force. And I have another way to initialize the positions and another way to update the positions, which now follow the wave function. So this is the way we would implement importance sampling. Now, if you scroll down in the slides here, you will find some of the basic programming elements, which we will also pick up next week. But you could also take a look at these. And then we are going to also look at the mathematics of the Fokker-Planck equation and the Langevin equation. And this is where we are going to stop today. And so next week, we are going to look at the mathematical details of Fokker-Planck sampling, the Fokker-Planck equation and the Langevin equation, and also look into more details into these specific programming elements when we also have a correlated part of the wave function. Now, in our case now, and this is what I want you guys to start looking at, in particular if you're collaborating, you can distribute the jobs among yourself, is to find the quantum force for the simple harmonic oscillator function, either with one particle or more particles, because these are quantities you will need when you now are going to set up the quantum force. Okay, so we're going to stop the recording here. And I said, I invite you to take a look at the material after this program, but we will cover this material also next week because we need to discuss in more detail the Fokker-Planck equation and the Langevin equation.